Hello, my name is Dr. Andrew Seeley. I'm the Director of Advanced Formation for the Institute for Catholic Liberal Education and also a tutor at Thomas Aquinas College in California. I'm happy to welcome you to this series of talks on math, ancient and modern, which completes our Advanced Formation summer webinar series. Hope you've enjoyed some of the other talks and that you'll enjoy this one. We did record these live, but my talk didn't turn out so well in terms of the recording, so I'm re-recording this to empty space right now. But I hope you'll enjoy it, and I hope it'll be maybe even better than the first time around. I was very gratified to see the strong interest in these talks. We had over 200 people register for this day of talks, and many were able to join us live. Many more really asked to see the recordings. So I think that shows a great interest in this topic, especially because the mathematics and the sciences have, in modern times, been seen as outside of the humanities disciplines, and so not connected to the liberal arts education. And one of the things we hope to address here is to show how the humanities and the sciences were considered by ancients and medievals as integral to the fully freeing education that the liberal arts ought to provide. And we want this to be a part of helping the classical liberal arts revival to breathe again with both lungs, with the humanities and the sciences. When I was a student at Thomas Aquinas College, which is it's a liberal arts program, and I would tell people I was doing a liberal arts program, I'd always make sure to say, you know, we're doing theology and philosophy, literature, math, and science. We do 4 years of math and science because I didn't want them to think that it was all a bunch of basket weaving. But that's the ancient traditional view of liberal arts education, that it begins with the trivium, the disciplines ordered to perfecting our use of language, but it culminates in the quadrivium, the 4 mathematical disciplines of arithmetic, geometry, music, and astronomy. I'm going to begin this series by talking about the ancient view of mathematics, and I want to look at it through the lens of Ptolemy, the great astronomer, and Euclid, the great geometer. And then Dr. Arthur Hippler will be focusing on the algebraic training that dominates high school education, in fact, dominates all mathematics education now, and what formative effects and that can have on the mind. And then Dr. Merrill Roberts will be looking at how modern mathematics and modern approaches can open up the wonderful world of modern science. We hope that this will be a learning experience for you that's worthwhile for its own sake, and will encourage you, if you are not if you don't feel well versed in mathematics, to learn more, to engage in it more yourself. We also hope that it will help you take advantage of, though we would like to see a curricular reform of the math and science programs that would be in line with the classical liberal arts ideals. Still, until that happens, this will help you take advantage of opportunities in your own current situation to approach math and science in a healthier, more liberal and freeing way for the students and for yourselves. We also hope that this will begin a dialogue that will help us prepare to make, as an institute, to make more concrete curricular suggestions and promote those who are taking good paths, we think. Okay, so let me begin by introducing an ancient look at the quadrivium, the liberal arts, and to see how they understood their freeing character. And I want to start with Ptolemy. As I said, Ptolemy was the great ancient astronomer whose work called the Almagest in the 2nd century AD became the text for astronomy, just like Euclid's Elements were the text for geometry. Ptolemy's astronomy was used for 1,500 years. It was highly accurate, and in fact, I think it was used in even training of naval personnel up until at least recent times as a more intuitive way of being able to determine the positions of the stars in the night sky than a Copernican model. So let me begin by taking a look at the preface to Ptolemy's Almagest. And over here. So Ptolemy, one of the reasons I want to look at Ptolemy is because he has a preface in which he explains why he's taking up the mathematical disciplines, why he's chosen to do that, and why he's chosen to do astronomy in particular. Not many mathematicians, the ancient mathematicians tended to say what they were doing or why they sort of plunge you into it. But Ptolemy does talk about this. And it's striking that in his preface, he begins by talking about the true philosophers. This is whom he's addressing. He's talking to the true philosophers. So he sees what he's doing as a part of the pursuit of wisdom. He might think of wisdom as a comprehensive, unified understanding of everything. And that Ptolemy immediately talks about the division of philosophy into the theoretical and the practical. So a comprehensive, unified vision of everything can be of everything that man can do, having an understanding of the goals of human life and how best men can act to bring that about. And that's the practical part of philosophy. Or it can be a unified understanding of everything that has been done by someone else. It's not anything we can change, nothing we can affect. It's all been done before us. And then it's theoretical. Theoretical comes from the Greek word theorein, which means something like an intent gazing on something, to try to take it all in, to grasp it in its details, but also in its beautiful wholeness. So he says that, hence we thought it fitting to guide our actions in such a way as to never forget, even in ordinary affairs, to strive for a noble and disciplined disposition, but to devote most of our time to intellectual matters in order to teach theories which are so many and beautiful, and especially those to which the epithet mathematical is particularly applied. So it's striking here that it says, yes, we want to live our life in a noble way, but I have chosen to devote most of my time to intellectual matters, to the beautiful theories the beautiful gazes that one gets upon a reality we can't affect, that we don't make ourselves. And that's how he understands mathematics. Mathematics is among those life choices that we make to learn about the intellectually beautiful. So it's striking that he presents this as a choice. The question is, what shall I devote my life to? What shall I, in the time that I have where I don't have to be forced by necessity to take care of things, what is it that I should devote my life to, devote my time to? Should I just devote myself to a life of pleasure without thought? Should my thought be devoted to how to live and how to achieve the maximum good in my life? Or should I be devoted to a life of thought about things that can only be thought? Ptolemy, along with the ancient philosophers, chose to always seek the intellectually beautiful. And in this way, you can see part of the freeing character of the mathematical arts as they understood them. For one thing, and importantly, the liberal art, the quadrivium, is meant to open up the mind to realize the intellectually beautiful exists, that there is something that's worth understanding for its own sake, even though it's apart from any use or good that that might give to us. And in this way, we see that the ancients were in a very similar spirit to that of Mary in the gospel stories, who chose the better part to just listen to Jesus. Samwise Gamfast in Tolkien's Lord of the Rings looks up at the stars in the midst of Mordor. He sees a star, and it comforts him to realize that there's something beautiful forever beyond the reach of evil. And that is something that the ancients found in mathematics, in the study of mathematics. C.S. Lewis, in his essay, Learning in Wartime, talks about the way men are different from other animals, from the ants in particular. Men propound mathematical theorems in beleaguered series, conduct metaphysical arguments in condemned cells, make jokes on scaffolds, discuss the last new poem while advancing to the walls of Quebec, and comb their hair at Thermopylae. This is not panache, he says, it is our nature. And I think that we see that a terrible effect of never introducing the young to what is simply intellectually beautiful and worth knowing and worth spending time of your life to capture is that our nobly minded youth think that the only thing that's worth doing is acting so as to change the world. And so they long for somebody to give them a change that they can throw themselves into. And that often ends up leading to societal disasters. Now, Ptolemy goes on to talk about the difference between why he chose to study mathematics as opposed to the other branches of ancient philosophy, the theological, the inquiry into the divine, and the physics, the study of simply of the natural world. And he says that the subject matter of mathematics falls, as it were, in the middle between the other two, since first it can be conceived of both with and without the aid of the senses, and secondly is an attribute of all existing things without exception, both mortal and immortal. So we see in that first part, mathematics, he says, can be conceived of both with and without the aid of the senses. So when you're doing math, at least when you're doing math as the ancients saw it, you have an image that you're working with, something that you can see. And yet, you realize that you're not thinking about that particular thing that you've drawn. What you're thinking about is something that your mind sees even when your senses don't. And we'll see some examples of that as we turn to Euclid. So it's something that, unlike the theological, which is simply known with the mind, the senses don't help us and only distract us. Mathematics is very visual, it can be even tactile. At least though there are visual aids and tactile aids for it. But unlike the study of the natural world, the mathematical objects have a perfection that only the mind can see. So it has this middle character. We also see there in that quotation that he says, its subject matter is an attribute of all existing things without exception, both mortal and immortal. And here we see a way in which ancient astronomy is going to be very different from modern astronomy, because the ancients tended to think that the things of the heavens, the stars, the planets, the sun, the moon, that those were eternal bodies that never would change. They existed forever, and they'll go on existing forever. And so they're immortal, and so they're either divine themselves, or they're perfect images and instruments of the divine. So we can see, at least for the ancients, they thought that they could see the divine God, the gods at work directly in the motions of the heavens. Okay. It's the loss of this sense of the immediacy of the divine, the visible immediacy of the divine, that C.S. Lewis addresses in his book, Discarded Image. There's another book by Michael Ward about C.S. Lewis and his Narnia Chronicles called Planet Narnia, that in which he talks about how C.S. Lewis was trying to recapture, remythologize the heavens for us, because he saw how much we had lost in it. Okay, and then Ptolemy goes on to talk about another reason to study mathematics, that he says, are connected with those. He says, only mathematics can provide sure and unshakable knowledge to its devotees, provided one approaches it rigorously. For its kind of proof proceeds by indisputable methods, namely arithmetic and geometry. So another aspect of the freeing character of the study of mathematics is that it gives those who are devoted to it sure and unshakable knowledge. That gives them certainty. It gives them something that's unshakable. It also, but only if those who are devoted to it approach it rigorously, approach it in a methodical way. So in studying mathematics and being trained in mathematics, the young are being given a taste of what it means to really know, and the difficulties and the commitment that real knowledge demands. And finally, Ptolemy goes on to talk about why he chose to study astronomy in particular. He says, this science, above all things, could make men see clearly. From the constancy, order, symmetry, and calm which are associated with the divine, it makes its followers lovers of this divine beauty, accustoming them and reforming their natures, as it were, to a similar spiritual state. It is this love of the contemplation of the eternal and unchanging which we constantly strive to increase by studying those parts of these sciences which have already been mastered by those who approach them in a genuine spirit of inquiry. So Ptolemy felt that by studying astronomy, he was arousing himself to live more nobly in the things that he could govern in his own life, because in studying the stars mathematically, he discovered and revealed to others a constancy, order, symmetry, and calm. I think that's really cool. Now, I don't know if that actually, to what extent that actually made its, or inclined its devotees to live more virtuous and noble lives, but he shows you what it ought to do. If you see that this is the way the divine reveals itself in the constancy, order, symmetry, and calm, then that should inspire you to want to live that way yourself. So then Ptolemy shows us reveals his choice to study mathematics, in particular astronomy, because of its intellectually beautiful gazings through its theorems, its attention to objects which are perfectly knowable and yet eternal, because you can have, especially for the young, you can achieve real knowledge and experience what real knowledge is and what it takes to have real knowledge. And finally, because it increases the love of contemplation, of just seeing and understanding things that are worth knowing for their own sake, which has an ennobling effect on the character. Now, astronomy can no longer be for us, as I said, what it was for the ancients, but Euclid, the study of Euclid, offers us many of the same benefits. So let me, I'm going to give you a little introductory tour of Euclid. I'll flip over here. And then talk about its liberating character. So we're going to start with one of my favorite websites, this Euclid's Elements from Math at clarku.edu. Let's start that over. I want to introduce you to one of my favorite websites, which contains all of Euclid's Elements. And and I'll have this link and other resources to share with you when we send out the recordings. But this website contains all 13 books of Euclid's Elements. And so we can see it has 13 books. The first 6 of the books deal with let me start this over again. Okay, I want to give you a tour of Euclid through using one of my favorite websites. This one has all of Euclid's Elements, and have this link and other resources available to share with you when we send out the recordings. We can see that Euclid's Elements consists of 13 books. The first 10 of the books deal with what we call plane geometry, just the geometry of figures that are flat figures. The last 3 introduce us to the geometry of solid figures. And this first book, in the first book, Euclid introduces us to a study of rectilinear figures, figures bounded by straight lines, and particularly shows you how we can understand those figures by resolving them to triangles and squares. And he begins by giving us a series of foundations, by grounding us in a series of definitions, what he calls postulates and common notions. These definitions are of very, oh shoot, I'm in book 3. Okay, I'm going to give you a tour of Euclid, a brief introductory tour of Euclid's Elements using this website, which has the entire text of Euclid's Elements along with diagrams. And this link, along with other resources, will be available, and we'll send it out to you along with the recordings. So we can see Euclid's Elements consists of 13 books. The first 10 books are devoted to the study of plane figures, just flat figures, and books 11 through 13 are devoted to studying 3-dimensional figures, as solid figures. And let's take a look at book 1. In book 1, Euclid is focusing on the study just of rectilinear figures, figures bounded by straight lines, and he shows you how you can understand them by reducing them to triangles and squares. And he begins by laying the foundation before he gets into any of his theorems or propositions. He gives us definitions, postulates, and common notions. He defines many things which he'll be talking about: the point, the line, the straight line, angles, plane angles, obtuse, acute, right angles. A circle, definition 15 gives us a definition of the circle, parallel lines in definition 23. So he gives us, as a starting point, clear definitions of what he's going to be talking about. Then he goes on to postulate certain simple truths or certain simple claims about what can be done that have nothing more simple than they are to ground them in. So these are going to be the basis of his arguments going on. So the first postulate, to draw a straight line from any point to any point. You can't get more fundamental. You can't prove that you can draw a straight line from any point to any point by anything more simple. To describe a circle with any center and radius, that's postulate 3. Postulate 4, that all right angles equal one another. So those are the simplest truths that he can find, along with what he calls common notions. The postulates deal with truths about geometrical figures. Common notions are truths that apply to all mathematics. Things which are equal to the same or equal to one another. If equals subtracted from equals and the remainders are equal, the whole is greater than the part. Now, what should be striking about all of these is that they're simple, straightforward, well expressed, and they're understandable by the young mind. Even a young teenager can understand these things and say, yes, I see that these things are true. I see that I understand what's being told me, and I can use this as a beginning for coming to know something. And they're not dependent on Euclid's authority or anybody's authority. And they should be able to see that this isn't just Euclid's game. When Euclid says that things which equal the same are also equal to one another, this is something that every individual affirms for himself as being true. So that this isn't Euclid's game, this is everybody's game. It's the way that we think about the mathematical world and mathematical realities. And then he goes on in his propositions. He starts with constructing an equilateral triangle on a given finite straight line. He goes through a number of, actually 48 propositions in this book to bisect a given rectilinear angle. This one, proposition 13, if a straight line stands on a straight line, then it makes either two right angles or angles whose sum equals two right angles. So he proves that when you have a straight line and you put a line like this, the two angles added up together equal two right angles. One of the exciting things for those who've done math before is that he proves many basic formula, like in proposition 32, he proves that for any triangle, the sum of the three interior angles is equal to two right angles. We know the formula that the angles of a triangle equal 180 degrees. Now, Euclid never talks about it in terms of degrees, but he says when you add up the angles of any triangle, the three of them together equal two right angles. So that formula, he shows how that formula is grounded in those very basic assumptions that he laid out at the beginning. Proposition 35 is one of my favorites. This is parallelograms which are in the same base and then the same parallels are equal to one another. So in this proposition, he shows that parallelogram ABCD is equal to parallelogram EBCF. Now, this is another common formula, or at least it's connected to one, which is that the area of any parallelogram is equal to the base times the height. And that's because if you erect a rectangle right here on base BC, this proposition shows you that the parallelograms are all equal to this rectangle. And so that when you drop the height of the parallelogram, that's one of the sides of the rectangle. So the parallelogram is equal to the base times the height is proved through this. And you kind of see how the proof goes here. He starts this proof by showing that these two triangles, ABE and DCF, ABE and DCF are equal to one another because they're just the same shape. You could push over that way. That's not his argument, but you can see it yourself that those two are the same. So then if you take away this common area, then you have two equal four-sided figures, A, D, G, B, and E, G, C, F. And then you can add back in this triangle here, because equals added to equals are equal. And so then you get your two parallelograms, which are equal. I think it's neat. This proposition is neat, one, because it proves a common formula. You can see how visual it is, how you can see the equality. Not there's an argument that shows you that they must be equal whether you see it or not, but you can really visually see the equality, see the steps of the argument. Also, it's really neat to realize that if you extend these parallels out as far as you want, and you create a parallelogram that would be dragged as thin as you please, as long as it's still within the same parallels and on the same base, that really long, skinny parallelogram is equal to either of these two fatter parallelograms. And that shows you the power of the argument, that you can see even when things don't look to be equal, the argument can show you they must be equal. So the mind can see things that boggle the imagination even while it's using the imagination. I wanted to take a look at the culminating, the book culminates in the argument for the Pythagorean theorem, which I want to take a look at in a moment. But in right-angled triangles, the square on the side opposite the right angle equals the sum of the squares on the sides that are containing the right angles. So that a squared plus b squared equals c squared, and is something we may have, place where we encountered the formula. Come back to that in a minute. I want to show you a few other things. In book 3, Euclid devotes his book 3 to the study of circles, and there's so many cool things he reveals about circles. One of them is that there are tangent lines. This, never mind, cut that out. Okay. Okay, come back to the Pythagorean theorem in a moment. I want to show you, quickly take a look at book 3. In book 3, Euclid focuses on circles and on revealing the beautiful properties of circles. Among them is this proposition that in a circle, the angles in the same segment are equal to one another. So in this proposition, he shows you that all the angles that stand on the chord BD, so the angles like BAD and BED, they're all equal to one another. So wherever you put an angle in this circle, even real close like that, those angles are all equal to one another. So it's amazing to think about that. And then later on, he'll prove that all of the angles in a semicircle are all right angles. So if you draw this through here, all the angles that you put there are all equal to right angles. That's really cool. In book 4, then, he takes his, where'd my book 4 go? There we go. In book 4, he then takes circles, the rectilineal figures of book 1 and the circles of book 3, and puts them inside and outside of each other. So in his culminating proposition, in proposition 16, he inscribes an equilateral and equiangular 15-angled figure in a given circle. So here's your circle, and then you have to divide it into 15 segments. All of those segments have to be equal to one another, and all the angles that they form are equal to one another. And you can see in this that he's going to use a couple of things he's already shown us how to do: how to stick an equilateral triangle in a circle, and how to stick a regular pentagon in a circle. So that's what he does in book 4. And then when we jump to give you a sense of some of the solid books, in book 12, he has this neat proposition which students tend to call the Death Star proposition. And in this proposition, he takes two spheres, the blue sphere and the green sphere, and he inscribes a polyhedral solid, that is a solid with flat surfaces. He inscribes a polyhedral solid within the larger sphere, but in such a way that it doesn't touch the inner sphere. And in this diagram, that doesn't look too hard because there's a lot of space between the two. But his argument shows you that even if this blue sphere grew to be imperceptibly close to the green sphere, he would still be able to stick a flat-sided solid all around in there. And that's a step towards helping him to, in book 13, inscribe the regular solids within spheres, just as he had done in book 4, inscribed regular plane figures in circles. In book 13, he inscribes the regular solids that within the spheres. So that's pretty amazing. Okay, so that's a general look at Euclid. Now I just want to take a brief time to look at one of the propositions. In this one, we're going to look at proposition 47 of book 1, which is known as the Pythagorean theorem. In right-angled triangles, the square on the side opposite the right angle equals the sum of the squares on the sides containing the right angle. So that's the beginning of the proposition. So the first thing that Euclid does is he enunciates, it's called an enunciation. He states exactly what he's going to prove. He states exactly what he's going to prove in just the right language for what he's going to do. This is part of learning how to make an argument, to know exactly what it is that you're trying to prove, and recognize that other things might come up that are interesting, but if they're not relevant to proving this truth, then you don't want to bring them up in the argument. This is not time to talk about them right now. When I'm teaching Euclid, I insist that my students, when they make their presentations of the propositions, give the enunciations word for word. They don't have to give his arguments word for word, but they do have to give the enunciations word for word. Now then, he takes that universal enunciation and he makes it concrete and particular. So we're not going to be thinking just generally about right-angled triangles. We're going to be thinking about this one, the one we draw, or at least the one that the drawing images for us. So ABC, and then Euclid draws squares upon them on the sides. And so we're not talking just abstractly about A superscript 2 plus B superscript 2. We're actually talking about and looking at squares that we can draw and look at. By the way, this is, I am using this PowerPoint presentation from Sandy Bultina, who also has a wonderfully helpful series of videos in which she goes through all of the propositions in book 1 of Euclid for those who are eager to try to work through Euclid's book 1 on their own. So you actually draw the squares, and we're looking and thinking about particular squares here. So it's kind of the experience of the concrete character of mathematics and its visual character. And then, so that's what we're going to try to prove. And then Euclid does something which we might not realize we need to prove. Because when we put these squares on here, it looks like we've got straight lines. We might assume that that's just a straight line. But we didn't make this as a straight line. We didn't take CA and extend it out there to make the side of the square. We stuck the square, we constructed the square on this side. So we don't know that this is a straight line. Euclid sees this as a matter for proof. So this is a way in which Euclid is training the mind to see to make us aware of what we're assuming that we should be proving. Oftentimes it's not clear. We're ready to assume things because they look right. So he gives us an argument that, oh, they must be on a straight line because we have a right angle from the right angle triangle next to a right angle from the square. And back in proposition 14, he had argued that whenever you have two right angles set up next to each other, then the resulting sides form a straight line. So he's proven that. He does that for both sides. And then when we get over to here, actually go back to here. So then the next step in his strategy is to take two triangles, ABD and FBC, and prove that they're equal. No. Okay, Chris, cut that little bit out, and we'll go here. So the next step in Euclid's strategy is to divide the larger square into two by dropping a parallel line. So we now have that larger square consists of two rectangles, BL and LC. And his strategy is to prove that this rectangle is equal to this square, and this rectangle is equal to that square. And he's going to do this by proving that two triangles are equal, ABD and FBC. And those two triangles he shows are equal because they have two sides that are equal. FB is equal to AB, and BD is equal to BC. And the angles between them are equal. The angles around B are also equal. So you could take those two triangles, you could take this one triangle and flip it over, and it would lie on top of and perfectly coincide with that. So the two triangles are equal by what we call the side angle side theorem, though Euclid proves it in proposition 4 of book 1. And then he points out that those two triangles are equal, but each triangle, say triangle ABD, is in the same parallels as the rectangle or the square. And since this triangle then is equal to 1/2 of this rectangle BL, FBC is equal to 1/2 of the square FA. So since the square is double of one triangle and the rectangle is double of the other triangle, the two triangles are equal, then the two rectilineal figures are equal. So that's the square and the triangle, and the rectangle and the triangle, and so the two figures are equal. And so then he's going to be able to do the same thing on the other side with the same proof. And so then you have your completed theorem. Now, even though that whole argument was done looking at and thinking about a particular figure, and then Euclid draws the conclusion about that particular figure, yet none of the steps in the argument are dependent upon any of the particularities of that figure. So that means that he can say generally, anytime you have a right-angled triangle, no matter what it looks like, the same steps will prove the same truth. And so while being able to think through the argument in the concrete and visual particular, we're also coming to the universal truth. Okay, so I hope that tour of Euclid will help you to see that many of the characteristics that Ptolemy pointed out about astronomy would be true about Euclid as well. Euclid contains many beautiful theorems which speak to the intellect alone. And Euclid's work is just the elements. It's just the launching pad. There's so much more in mathematics that's more complex and more beautiful that Euclid is the gateway for. So it's a life-worthy choice to say I want to take a lot of my free time and devote it to this kind of mathematical study. I think you can see that for the student of Euclid, they're gaining a real experience of knowledge. They can gain unshakable certitude about the truths that he presents. The object is imageable and so knowable. But their objects are perfect. They're not approximations. And even when we draw them badly, we can use even bad images to help us think about the real thing we're thinking about, which is something perfect. We're not dealing with approximations, which is often the only thing you can get when you're working with concrete material things. The Euclid's propositions are grounded in what's immediately known and imaginable premises. Through careful, rigorous argumentation, with all the relevancies left aside, with an enunciation which states exactly what I'm trying to prove, without leaving out any steps, giving us no unnecessary information, we can achieve real knowledge. We have clarity everywhere. It's a wonderful thing with Euclid discussions that among students that there'll be challenges to Euclid steps that will come up. And usually students will end up by explaining it more carefully, everybody will come to see, oh, I see what he was doing, and they come to agreement. So it's a great experience of actually coming through disagreement, coming from disagreement through conversation to universally accepted knowledge. And we can also see that Euclid is not teaching us about an order made by man. There is something of experience, getting knowledge of what's constant, the orderly, the symmetrical, the calm that Ptolemy mentions. Remember, when I was a freshman, when I was a sophomore, a student who had recently graduated that I'd gotten to know came back for a visit, and I asked her what she most missed about the studies, and she said Euclid. She said, every once in a while I just get out Euclid and I read a proposition, because the world is so gray and nebulous, and you're just never sure about whether you're doing the right thing or not, and you just open up Euclid and go through a proposition, and it brings peace and calm to the soul. I think that it's also, we see the liberating character of the study of Euclid in that we see that a truth can be known. It's not relative. For me, as a student of Euclid, going through all the steps of book one, culminating in that Pythagorean theorem, gave me an experience of knowing something which in high school had only been told to accept and just use that Pythagorean theorem in order to solve equations, without any concern for what it meant or whether it was true or not. That I came to see it through working through all those propositions. I came to see it and to know it for myself. That was a huge boost to my faith, because I thought, I see now that not all truth is relative. We also experience that knowledge makes demands. Working through Euclid, especially when you're presenting to others and open to having to answer questions, it accustoms you to giving reasons and seeing your mistakes and correcting them, to being careful and thorough. I think it's also important to see that when you develop the habit of presenting Euclid, not just reading it, but also being able to represent it yourself, that it trains your memory. It trains you in being able to memorize through coming to a deeper understanding, through analyzing an argument into its major parts, and also to seeing a presentation that's according to the order of the things themselves. So for modern mathematicians, often the only important thing really is discovery. Discovering different mathematical truths. The presentation of them once discovered, which was what Euclid is all about. Euclid doesn't tell us how he discovered his propositions. He just presents the truths discovered. That's, for many modern mathematicians, that's irrelevant and slavish. But I think with Euclid, you get accustomed to seeing, presenting in an order that's according to the nature of the things themselves. And I hope that you get a sense of the fascination that Euclid's arguments offer to us. A fascination which removes us above the petty things of life, a fascination with the things we're thinking about. You know, what are these things anyway? How can we know them? Which itself is a fascination with ourselves. How can we know these truths? And so let me sum up this presentation by suggesting some questions for you as you're doing mathematics for yourself, as you're doing mathematics with students, that would help you to see whether you're approaching it as a liberal art or not. Does your study of mathematics, does it free you? Does it free your students by introducing ourselves to intellectual beauty, by giving experience of knowing, by training in careful reasoning, by opening to wisdom? And finally, let me conclude by referring to Abraham Lincoln. We have a passage from Carl Sandburg's biography of Abraham Lincoln that recounts how, when a young lawyer tried to sharpen his reasoning skills, the largely unschooled Lincoln Let me conclude by referring to Abraham Lincoln as an encouraging example. We have a passage from Carl Sandburg's biography of Abraham Lincoln that recounts how, when a young lawyer trying to sharpen his reasoning skills, the largely unschooled Lincoln bought the Elements of Euclid, a book 23 centuries old. It went into his carpet bag as he went on the circuit. At night, he read Euclid by the light of a candle after others had dropped off to sleep. It has often been noted that Lincoln's prose was influenced and enriched by a study of Shakespeare and the Bible. It is likewise obvious that many of his political arguments echo the logical development of a Euclidean proposition. So there you have it. Lincoln, formed by the trivium through reading Shakespeare and the Bible, and the quadrivium through his study of Euclid. Thank you.